This is on lesson 3.3 about finding complex solutions of quadratic equations. So, if you recall in our previous lesson, we talked about solving things of the form ax squared plus c equal to 0, basically where the b value is 0. Today we're going to generalize and talk about solving things of the form ax squared plus bx plus c equal to 0. This lesson begins with an exploration, and I'm going to omit that in the interest of time and just present the major results as facts. If you were interested in how you could come up with these facts on your own, you could work through the exploration at the beginning on your own, but it's not something I'd ever ask you to be able to repeat on your own. So the first fact is the minimum or maximum of a quadratic function occurs at x equals negative b over 2a, and the minimum or maximum value of that quadratic function is f of negative b over 2a, and 3, it's a minimum if that a value is positive, and it's a maximum if the a value is negative. And 4, we can also predict how many and what type of solutions. So if b squared minus 4ac is less than 0, we have 2 complex solutions. And by complex here we mean we have an I in it. And if b squared minus 4ac is equal to 0, we have 1 real solution. And if b squared minus 4ac is greater than 0, we have 2 real solutions. And as a piece of vocab here, this quantity, b squared minus 4ac, this is called the discriminant. So you might see that piece of vocab. So, we'll circle back to these and show you how to use them in a minute. Actually, let's do that right now. Highlight. So, let's say we find the minimum, maximum, and number of solutions. 4. Since we're doing that together. And let's say x squared minus 10x equals 0. So that minimum or maximum occurs at negative b over 2a. My b term is here, and my a term is here. Remember, since there's nothing written, the coefficient there is really 1. So I have negative 10, and then 2 times 1. So that gives me 5. And the maximum value then is going to be f of 5. So I'll just plug 5 in for all my x's. So 25 minus 50 minus 7 is negative 32. And then since the a value is 1, and this is positive, it means what we found is a minimum. And that minimum is the 0.5 negative 32. And then the number of solutions I can find by doing b squared minus 4ac. So that's negative 10 squared minus 4 times 1 times negative 7, or 100 plus 28. And clearly this is bigger than 0, so I'd say 2 real solutions. Hopefully that's okay. Again, I got 2 real solutions by using this criteria. So now we'll move on. So a couple of things to remember here, that if I have a quantity squared like this is really the same thing as this, which when we FOIL, or a squared plus 2ab plus b squared. This is called the perfect squares factor and pattern. So our observation here is going to be that I can take something like this and solve this using our method from 3.2. So I can add 5 to both sides. Divide both sides by 2. Square root both sides. Subtract 3 from both sides. And then I need to simplify that fraction. So I'm going to use the quotient property to rewrite that fraction like this, and then rationalize the denominator by multiplying the numerator and denominator by the conjugate. And the square root of 2 times square root of 2 is the square root of 4, which is just 2. And if I really wanted to, this answer is okay, but I could make a common denominator here and write this all as one big fraction, which is kind of the preferred way of doing it. So why did I point out that we can still apply our old method from 3.2 on something that looks like this? Is because if I remember up here, this piece is really a quadratic equation in this form. So if I can find a method to go from something that looks like this to something that looks like that, then what we did in 3.2 can kind of take us the rest of the way to an answer. So, is there a way to do that? Yes. So the goal here is to go from something that looks like ax squared plus bx plus c equal to 0 to something that looks like a times something, I'm just going to leave that blank for now, quantity squared plus c equal to 0, and then we can just use our method from last section on this. The question is, how do I do this? Well, the name that we're going to give for this process is called completing the square, that I abbreviate as CTS. The idea will be to create a perfect squares factoring pattern. So let's just go through a numeric example, a couple numeric examples, until we kind of feel like we got the hang of this. So we'll start with this quadratic that we were looking at earlier. And remember, the goal is to try to get it into something that kind of looks like this. And the idea is going to be by creating a perfect square. So if we go back and we look at our perfect square factoring pattern, we have something, we need to make something that looks like this. So I'm going to do is I'm going to assume that I have my a squared as here. That's going to be like my a squared. I'm going to assume this is my 2ab. And then I'm going to make this part b squared by adding or subtracting from both sides. So let's see this done now. So if x squared is a squared, a must be x. And if a is x, then 2b has to be 10, because the a is the x part. So that tells me that b is 5. So now that I know this, I'm going to go and add b squared to both sides. And consider just this piece. This piece is now a perfect square. So I can factor this using my perfect square. So if I go back and look at what that said is, something in this form is equal to this, and I know what my a is, and I know what my b is, because I figured that out at the start. So this is going to factor to x plus 5 squared. And from here, I can just now use my square root of both sides. Don't forget your plus minuses. And if I subtract 5, this, but I recognize, hopefully, that the square root of 32, that there's a perfect square in there. In fact, 16 times 2. The square root of 16 is 4. So there is my answer. Now let's kind of formalize this completing the square step. So let's make this a procedure now that we just kind of follow. Step 1. So what we'll do is we'll start dividing both sides by a. And 2, we're going to add b over 2 squared to both sides. 3. Rewrite the perfect square using the factoring pattern. And 4, to solve using our method from 3.2. So, let's do this as an example. Notice that this first step seems like a new one. And the reason that was because if I look at the problem I was given, that our coefficient here was A. Or was 1. So there was nothing really to do with that first step. So, let's say that we have 3x squared plus 9x minus 6 equals 0. So, for step 1, we say divide both sides by 3. So if I divide the left side by 3, since its division is distributed, I get then x squared plus 3x minus 2 equals 0. And now I'm going to add, here's my new b value, I'm going to add b over 2 squared to both sides. And by 3 b over 2, I really mean 3 over 2. Okay. Now, this piece here is by very definition a perfect square. So the first term is x squared. The last term is 3 over 2 squared. So I can use those to just say it's plus 3 over 2 squared. And then 9 over 2 squared is just 9 over 4. Where I squared the top and squared the bottom. So, again, what am I doing here? If I go back and look at my perfect square factoring pattern, it is way up here. A squared plus b squared is all I need to figure out that. And from here, I can now just use my method from 3.2. So I'm going to add 2 to both sides. So might as well make a common denominator. 2 is the same thing as 8 over 4. And I'm going to square root both sides. Don't forget your plus and minus. And then I'll just subtract 3 over 2 from both sides. And I'm done. Now, completing the square, this is nice because, well, it works every single time. The downside is, well, it's a rather lengthy process and maybe isn't that easy to do, but the pro, again, that it works every single time, is it's the exact same process every single time. So, because it's the exact same process every single time, I can do this just once and I can come up with a formula. So let's do that. So I'm going to just solve this very, very general situation. Again, this is any quadratic. And if I solve this, say, completing the square, I'm going to get a formula that'll work every single time. Okay, so the first step is going to be to divide by this leading coefficient. So LC is just leading coefficient. And then I'm going to add this middle term squared to both sides. The middle term will be divided by 2 squared to both sides. So this part here now is a perfect square. So I can factor this to be x plus e over 2a squared plus e over a equals b squared over 4a squared. I'll just factor the perfect square and I'll get some simplifying. Again, b over 2a squared is b squared, 2 squared, a squared. And now I'm going to subtract c over a from both sides. But to do that, I need to have a common denominator. I need to multiply c over a by 4a. To make a common denominator here. I'll square root both sides, and because I'm square rooting both sides, I get a plus or minus, and if I use the quotient property, I can apply that square root to the top, and that square root to the bottom, and in the bottom, if I apply the product property, I get square root of 4 over square root of a squared. So I have plus or minus square root b squared minus 4ac all over 2a. And now if I subtract b over 2a from both sides, I get x equals negative b plus or minus square root quantity b squared minus 4ac all over 2a. Wait a minute. I recognize this. You may have seen this before. This is the quadratic formula. And but she didn't know where it came from, but this is where it comes from. So this is something we want to have memorized. This is very important. I would not ask you to re-derive it for me, so I wouldn't ask you to be able to repeat that process I just did in this most general situation. But I would expect that you have this memorized, and I would expect you're able to use it. So let's look at an example. So remember before, we solved 3x squared plus 9x minus 6 equals 0. Well, we can do that also using the quadratic formula. So, I have here that a is 3, b is 9, c is negative 6. So I just need to plug them in. X equals negative of negative 9 plus or minus negative 9 squared minus 4 times 3 times negative 6 all over 2 times 3 And when I simplify this, it's positive 9. 9 squared, negative 9 squared is 81. Negative 4 times 3 times negative 6 is negative 12 times negative 6, so that's positive 72 over 6. And then that's 163 over 6. And not 163, silly, 153. And the question is, can I reduce the square root of 153? Well, hopefully you remember from elementary school that if you add up the digits of a number, and that number is divisible by 3, then 153 is divisible by 3. So I know that there's a 3 that can get in that. So 153 is equal to 3 times, well, hopefully it was easy to see 51, and then 3 times, well, 51, that's also divisible by 3. That's 3 times 17. So I know that the square root, or the square root of 153 is the same as 9 times 17. You could have guessed and checked that on your calculator too if you would have been more comfortable doing that, but a nice little review of topics you've seen before. So I simplify this and I have 9 plus or minus 3 squared root of 17 all over 6. And if I notice now that 9, 3, 6, these all have a 3 in common. So if I divide each of them by 3, I can reduce this entire fraction to this, which, if you look, was the same answer that we got here. Whoa! It works. So let's do another example before we call it a wrap. So let's say that we have x squared plus 8x plus 12 equals 2x. So remember, to use the quadratic formula, it has to equal 0, but we don't equal 0 right now. We equal 2x. How are we going to remedy that? Well, it's easy. We'll just subtract 2x from the sides. Come on, not that hard. It's a trick question. And now I can apply the quadratic formula. X equals negative 6 plus or minus 6 squared minus 4 times a times c all over 2a. That's 36 minus 48 for 2. So I have negative 6 plus or minus the square root of negative 12. And if I remember back from lesson 3.2, square root of negative, I mean that as negative 1 times the square root of 12. And negative 1, that's the same thing as I, like that. Now I got to check to see if there's a more simplifying I can do in that radical. Square root is 12, well sure there is. And this is the square root of 4, and the square root of 3, and the square root of 4 is just 2. So we can say this is 6 plus or minus 2i square root of 3 equals 2. And then I notice that 2, 6, and 2 all are divisible by 2. So if I do that, I can reduce, and I get this. And that does it. So there's our technique to solve any quadratic equation. Preferred method, get the equation equal to 0, and then we'll use the quadratic formula. And we're done. Can I use this method on the things that we did in 3-2? Sure, but it's a little bit of an overkill. It's like trying to swat a fly with a pistol, but, you know, you can do it. It's a little bit more than you need.